One of the highlights of IAU General Assemblies, at least the recent ones, is always this Gruber lecture, because you've heard yesterday how the Gruber Prize has been selected, and you've heard of the three people that have been selected this time, Wendy Freedman, Kennicutt, and Jeremy Mould, for their measurement of the Hubble constant with the Hubble telescope. So today we have the great pleasure of hearing directly from them news about how they arrived at this momentous discovery. So I invite the recipients of the prize, Wendy Freedman, Kennicutt, and Jeremy Mould. I understand they are going to speak in stages and pieces, and it's probably going to be an absolutely fascinating hour.
First thing I realized is not much point for a laser pointer, I guess, for this talk, so even though one's here. Yeah, screens on the side. Well, welcome, and thank you very much for sacrificing a little bit of your lunch break to hear our talk. We will try to be quick so that you don't starve today. We're going to try something that actually Saul Perlmutter and Brian Schmidt did 2 years ago when they gave the Gruber Prize lecture, and they actually did what is known in U.S. and professional wrestling language as a tag team of combining, going back and forth, sharing a single talk. Like measuring the Hubble constant, this is a process that will not be perfect, I'm sure, but hopefully will be informative and entertaining for you. If we could go to the next slide. Oh, I have the next. I can do that. So we're going to begin with an introduction and historical background. So this story actually goes back nearly 25 years to the mid-1980s. For those of you who are of our generation, I've given you a few visual cues for what this time was like. If you're from America, you'll remember this of the age of Rambo and Back to the Future. If you lived in just about any other country in the world, you will remember 1986 as the time of the hand of God, or if you lived in England, the hand of Maradona deciding the World Cup final. More relevant to the theme is the right-hand slide, shows two individuals who may be barely recognizable today. The gentleman on the left in the image is actually sitting over here. This is Jeremy Mould in an earlier geological time. The gentleman on the right is Mark Aronson, who was the original PI of our project. Mark unfortunately did not live to the completion of his project, and basically what we're going to tell you today is the story of how Mark's project unfolded, which of course we took over as a threesome when that became necessary. The quote at the bottom is from the another prize that Jeremy and Mark won, the Pierce Prize in the U.S., in which occurred about the time close to the launch of the Hubble Space Telescope when these plans were all set into motion. Now, today, people are fond of using the term precision cosmology, the idea that now, in a miraculous fashion in the last 15 years or so, we seem to have measured many of the primary cosmological parameters, including the Hubble constant, to within accuracies of a few percent. It was not long ago, in fact, the mid-1980s, when the situation was entirely different. This graph from John Huckra shows the progression in the value of H0 from Hubble's first measurements in the 1930s in a drop of nearly a factor of 10, 5 to 10, over the succeeding 4 decades. Even by the early and mid-1980s, the situation was not much better, and let's see if, here we go, animation works. Here's an expanded view of that plot, and I should, if this works, the animation, here's an arrow showing you roughly this time frame. Each of these symbols is a published refereed paper purporting to measure H0, and you see a dispersion of well over a factor of 2. This was one of 2 supreme embarrassments of the field before the advent the key project and the associated projects that went along with it. We did not know the size and age of the universe to better than a factor of 2. The other aspect of this embarrassment was nearly all of these values, even the low values, if you combined with the favored cosmological model at the time, which was a flat universe with dark matter and baryonic matter producing a closure density, that combination yielded a cosmic age, an age of the universe that was a few billion years less than the age of the oldest stars that could be age-dated in globular clusters. So it was an astrophysical dilemma as well as an observational one. The origins of why this problem existed is complicated to explain, but I'll give it an attempt. The methods that used at the time that we were following from the time of Hubble was the building of a classic distance ladder, as you see in the Eiffel Tower rendition on the right, in which you used Cepheid variables to lay out an accurate primary distance scale nearby, used those measurements to calibrate so-called secondary indicators, and of course used a variety of parallax measurements to calibrate the Cepheids. This is extremely difficult, especially back then, and the origin of the problem became coined by Alan Sandage, Gustav Tammann, as the twilight zone problem. The basic problem was there was a recognition around this time, starting with the work of de Vaucouleurs and others, that we lived in a highly structured universe, large-scale structure. This is the latest 2-mass rendition of the structure. That meant that if you wanted to measure a fair sample of the universe and measure the Hubble constant accurately, you had to extend your distance ladder. The tip of the Eiffel Tower had to extend to distances of order 100 megaparsecs. Complicating the problem was that we do not ourselves live in an average part of the universe. We live in an overdense region in the Virgo supercluster. The expansion in our immediate vicinity is retarded relative to the cosmic expansion, and yet another reason of having to extend far. So problem number one was you needed to calibrate well, let me explain. There's another diagram of the twilight zone actually from the Sandage and Tammann paper. To solve the problem basically was that you needed a set of secondary distance indicators that had very large reach and distance, but unfortunately the limit to which one could observe Cepheids from the ground was only a few megaparsecs, a few percent of that distance. There simply were not enough calibrating galaxies nearby in which we could measure Cepheids to calibrate the secondary distance indicators. Tully-Fisher relation, for example, I think had 2 calibrating galaxies at this time, supernovae only 1, and this gave room to large errors, random errors, and most importantly, systematic errors. The key to solving the problem, where Hubble Space Telescope comes in, was to use the superior resolution and the clear skies of Hubble, the ability to schedule time series observations in a very efficient manner, to measure distances of galaxies out to the Virgo cluster, basically, to 20 megaparsecs approximately at that time, and calibrate approximately 20 benchmark galaxies, galaxies that could be used to calibrate an entire suite of secondary distance indicators. So it's really a 2-step process. Here is the first step, actually, historically, was to go out and establish a series of secondary indicators. Some of the members of our team, for example, Jeremy, played major roles in calibrating, for example, the Tully-Fisher relation, but most of the calibration of the distant part of the ladder, the upper part, was done by other groups, and we'll be acknowledging several of those people when I come back later in the talk. So the concept was, first, from the ground, establish a set of secondary indicators that would provide relative distances out to 100 megaparsecs or farther, and then use Hubble Cepheid measurements to calibrate the 0 points of those methods: supernovae, surface brightness fluctuations, fundamental plane, Tully-Fisher relation, and so on. Notice where the emphasis is on redundancy, measuring lots of measurements. The keys to the key project were not only to make precise measurements, but understand the errors. Try to understand these systematic errors rigorously, so in a worst-case scenario, we could reduce those errors. The allocation committee was assigned to allocate key projects. One of them was decided to set aside a large block of time at the beginning of the Hubble Space Telescope mission to measure Hubble constant, and the committee set a benchmark that they wanted H0 measured to an absolute accuracy of plus or minus 10%, including the systematic errors. The last I'll be passing on in a moment. This flow chart, which probably only those in the front can read, is more detail on exactly how the experiment was designed. We measured, the key was Cepheid distances to, as I say, it eventually became about 24 galaxies that were calibrated, had supernovae that went off in them, or were Tully-Fisher calibrators, surface brightness fluctuation calibrators, and so on. Each of them yielded an independent measure, a semi-independent measure of Hubble. And then we had another second vital component to our project, and that was to make sure we understood the systematic errors in the Cepheid period luminosity relation itself, the Leavitt relation, including systematic dependences on metallicity. And that is my segue to Wendy, I believe, who will pick up the story there.
Okay, so the heart of the project was to measure the distances to a couple of dozen nearby galaxies to measure their period luminosity relations, and then thereby to calibrate these secondary methods. So the focus again was the Leavitt law, and this is the original period luminosity relation discovered by Henrietta Leavitt for 25 Cepheids in the Small Magellanic Cloud. She actually measured the maximum brightness and the minimum brightness for these stars, and with Pickering was able to establish this period luminosity relation. It was very difficult at the time to assess the systematic errors that would actually plague the distance scale for the decades to come. Part of the reason, of course, was photographic photometry was difficult. Photographic plates are nonlinear, and so it was decades before that was really realized, and the calibration could be replaced by photoelectric and then ultimately CCD photometry. The next was the fact that Cepheids are relatively young stars. We find them in regions where they're still nearby to the gas and dust out of which they formed, and photographic plates, again, were sensitive at blue wavelengths, and so measurements of Cepheids that were made in the early days was not yet possible to correct for this systematic effect, which only makes Cepheids appear fainter and therefore more distant. So here we had this luxury of the Hubble Space Telescope, and we had the opportunity to actually plan the observations in a way that it was not possible to do when people were making observations solely from the ground. So we didn't have the vagaries of weather, we didn't have to worry about moonlight, we didn't have to even worry about other colleagues on our telescopes who might have been scheduled on a given night if we wanted to make observations for these stars that had a range of periods. So Cepheids typically have periods in from 2 days up to about 100 days. The very long period Cepheids are very rare, so we tried to optimize for finding Cepheids up to about 60 days. So it had been known for a while that Cepheids in our own Milky Way galaxy, if you observe them at different wavelengths, the amplitudes of those stars are dependent on the wavelength at which you make those observations. So I'm just showing an example here from a Cepheid within our Milky Way galaxy, observed from the top at the ultraviolet through the blue and visual wavelengths, near infrared, out to 2.2 microns at the K band. So at the bluest wavelengths, the amplitudes are very large, and most of the photometry had been obtained at blue rather than ultraviolet wavelengths, and that makes it easier to find the Cepheids because their amplitudes are greatest, easier to find them against the background of the galaxies in which they reside. A clear advantage, however, of going to the infrared because the effects of reddening are much less severe at the longest wavelengths. So in order to make best use of the time on the telescope, we optimized by trying to pick a blue wavelength where the amplitudes of the Cepheids are relatively large, and then as far to the near-infrared as we could to take advantage of the smaller systematics because of the presence of reddening. So for HST, we settled on the V and the I band as a way to go forward. There was no ability to use HST at the time we made these measurements to go into the near-infrared. NICMOS came later, and we did, a subset of us, go on and observe the Cepheids with NICMOS. So the improvement to the Cepheid distance scale came, again, with the availability of linear detectors, specifically CCDs in the optical and near-infrared arrays, and then being able to go out above the Earth's atmosphere where the crowding was much less severe, the resolution was a factor of 10 times greater, the volume we could effectively survey was then 1,000 times greater, and there were only a handful of galaxies that had Cepheid distances that were useful for the calibration of the distance scale before HST, including the fact that for type 1a supernovae, which are the secondary method that we can observe to the greatest distances, there was not yet a single calibrator that was close enough to have Cepheids as well as supernovae measured simultaneously. One of the biggest improvements was the ability to correct for dust, and in fact, in the 1980s when we began obtaining CCD data, that was before the launch of Hubble, there were discrepancies at a level of a factor of 2 in the Cepheid distances alone. So on the left here I'm showing a plot for the galaxy M33. These are ground-based observations, in fact, taken at the Canada-France-Hawaii telescope. And these were distance moduli measured at blue visual, the R band and I band. The apparent distance modulus plotted as a function of inverse wavelength. And that's where we're first able to see, of course, the galaxy itself is at the same distance. Shouldn't depend, the distance shouldn't depend on the wavelength at which you make the observations. And the dashed line here is a fit to the interstellar extinction law. So if we can make measurements at multiple wavelengths, then we have the opportunity to correct for this systematic effect. I'm showing on the right data from NGC 6822. This is an irregular galaxy in the local group, but just showing for comparison, we actually now have observations that extend out into the mid-infrared with Spitzer, out to 8 microns. And so if you make measurements only at blue wavelengths, you're actually making an error in the distance modulus that is as large as 1 magnitude in this case. But by the time you go out to 4.5 microns, you're within 0.01 magnitudes of the true distance modulus to the galaxy. So that's skipping ahead a little bit to recent observations with Spitzer. But correcting for reddening is key. So again, just to remind you, we made our observations with the key project at V and I wavelength. That looked like a good way to go to optimize the amplitudes and decrease the reddening effects. And just to, difficult to remember the sense of this, and Larson has a cartoon of this. It tells you that objects in the mirror closer than they appear. That's in the sense that we had a very nice mirror, of course. It was orbiting the Earth in the form of HST, but if you don't correct for reddening, then you would overestimate the distance to the galaxy. So the next question was, how do we sample? And because we had this luxury of scheduling the observations in advance, we could actually determine how best to optimize for finding Cepheids that had periods in this range from 2 to 60 days. Now, of course, if we did it in a uniform way, then we could sample, say, a 50-day Cepheid every 5 days or so, 10 times, and then we would get a very good period for that 50-day star. But in order to optimize over the range of periods that we know exist, we had to come up with a strategy that would take advantage of the opportunity to schedule with HST and not use the literally hundreds of observations that had been done by people like Leavitt and Hubble and Sandage and others who didn't have this luxury of being able to observe from space. And that was one of the areas where, despite the fact that it was an awful tragedy with Challenger and HST was delayed, we had the opportunity in the 1980s to actually figure out how to do this sampling. And these are simulations that I'm showing from some work. This was a procedure that was actually developed by Barry Medor, I want to acknowledge this, to come up with a power law spacing to find these periods for a range of different Cepheids. So if you could optimize the slope of this power law, then you could actually avoid the aliasing that I'm showing here in the case, for example, of equally spaced or non-optimally spaced observations. And how did it work? You can see here, this is an example from two of the galaxies we observed, NGC 4414 and NGC 2090. And these are Cepheids with a range of periods shown here from 19 days up to 70 days. And there are some I-band observations shown in addition to the V-band observations. In fact, the discovery of the periods was made using V-band observations, and because then we knew the periods, we could use the I-band data, phase those using the periods obtained from the visual, and then make the correction for reddening. So we discovered over 800 Cepheids in the end, a sample of 18 galaxies, and the method worked very well. So what we would do in practice was pick a region in the outer parts of the spiral arms of these galaxies, come back to that same region, same pixels, use the same guide stars, observe them with this power law spacing 12 times in the V-band, 4 times in the I-band, and then either a year after the observations or a year prior to that sequence, we would take another observation just to nail down the periods at the long period end. We used two different programs for obtaining the photometry. One was All-Frame, developed by Peter Stetson, the other DuPhote, developed by Abhi Saha, who is here today. And we did double-blind tests. The whole nature, as we're hearing of this project, was to beat down the systematic errors and to do this as independently in as many different ways as we could. We aimed for a 10% overall accuracy, but at each stage of the project we were aiming for 5% so that ultimately we could be convinced that we had reached 10%. And this is a composite period luminosity relation. This is the I-band magnitude as a function of the period in days for the 800 Cepheids or so that we discovered as part of the project for the different galaxies shown there. The dispersion at the I-band empirically is 0.2 magnitudes, which corresponds to a distance uncertainty of 10%. So then in principle, if you have 100 Cepheids in a galaxy, you can make a 1% measurement. But of course, it's not just the statistical uncertainties, there are the systematics, and so that really is the name of the game, is try and beat down the systematics. So we observed a number of different distance indicators. We didn't rely at the level of the nearby galaxies on Cepheids alone, but we compared the distances to the HST Cepheid measurements with other measurements, including the tip of the red giant branch locally, Aurora Lyrae stars, the surface brightness fluctuation technique developed by John Tonry, planetary nebulae that had been studied by Jacobi and Chardulo. We looked at the globular cluster luminosity function, and in many cases the dispersion again was far less than the 10% goal we had set out to achieve, and in the area where there was overlap there was extremely good agreement in these distances, which gave us some confidence that we could go out to that next rung in the ladder. So let me turn now to Jeremy, who's going to talk about our metallicity calibration.
Okay, by now Wendy has convinced you that it can be made relatively straightforward to measure the distance of a galaxy using Cepheids and the Hubble Space Telescope. There is a subtlety, however. Not all stars have the same chemical composition, and differences in chemical composition mean that the period luminosity relation for Cepheids could be different in different places. And this led us to draw up a relationship between the true distance and the distance given by the period luminosity relation and a function of metallicity, which is shown in the first equation there. The distance inferred at higher metallicity is smaller as the Cepheids appear brighter. Now you may say, well, perhaps theory can help you with this, since stellar evolution covers the Cepheid phase, and since it's possible to carry out simulations of the period luminosity relation itself. However, two papers in 1993 and 1998 differed even in the sign for the coefficient there in metallicity in the period luminosity relation. those papers differing in the different opacities that were assumed. So we can say that the period luminosity relation dependence on metallicity is probably a small effect, but the theory is not predictive. So we undertook an empirical approach, and that is to study the galaxy M101. In M101, which has a strong radial gradient in metallicity, with a high metallicity range in the center and lower metallicity out in the outer spiral arms, it's possible to point the wide field camera at two regions, the central region there that you can see, and a region out in the outer parts, and compare the distance modulus, which should be the same, between the two fields. And we did this. First of all, I want to show you the radial gradient that is obtained from H2 regions in M101. You can see there the high metallicity oxygen abundance in the center, and 10 arc minutes further out, the metallicity has fallen by a factor of 10. So that's our test case, and we were able to assess that coefficient gamma using that test case. The inner modulus, the distance modulus for the inner field came out to be 29.2 with a 9% error, and the outer modulus, the distance modulus for the field in the outer parts, came out at 29.36 with a 0.08 magnitude error. So there we have a factor of 5 difference in metallicity, allowing us to determine at least roughly the VI coefficient gamma to be minus 0.24 magnitudes plus or minus 0.16 magnitude per factor of 10. Now that at least is a significant detection, but it's hardly definitive, and so we've looked at measurements of the Hubble constant with both a metallicity coefficient included and a metallicity coefficient absent. The oxygen abundance was measured for each of the key project galaxies in a separate project using ground-based telescopes, mostly published by Zaritsky, Kennicutt, and Hooker in the APJ. Another way of plotting this is to take the set of galaxies that we observed and use the tip of the red giant branch, that is the point on the red giant branch where the helium flash occurs, as an alternative standard candle. And you can see in the plot there that we've plotted the difference between the distance modulus measured with Cepheids and the distance modulus measured with the tip of the red giant branch, and different values of the gamma coefficient are shown. The central one there, the long dashed line, or rather the short dashed line I should say, is for using the coefficient minus 0.24, which we determined for M101, and that seems to be the best fit for the data, though the data are capable of bearing a number of different fits. So further evidence for a negative gamma coefficient of roughly minus 0.24. Another way of constraining this problem is to do away with Cepheids altogether and use the tip of the red giant branch distance indicator to calibrate the Tully-Fisher relation, the surface brightness fluctuations, and the other secondary distance indicators. And this works quite well. This is recent work that I've published, and it shows that if you calibrate the Tully-Fisher relation, that is plot luminosity or the h minus 0.5 luminosity versus the 21 centimeter velocity width, you obtain a relation using the tip of the red giant branch as distance indicator, which is the dashed line fitting the data there, and that's only slightly different from the calibration that Wendy's going to talk about in a moment, resulting from Cepheids. So all of this makes us think that we've got the metallicity dependence of the Cepheid period luminosity relation reasonably well in hand, and we can go on from here. And an update on this, a second galaxy in addition to M101 that we were able to study from the ground in work by Scowcroft and collaborators on M33 in rather the same way, taking a central field and the period luminosity relation for the Cepheids there, and an outer parts field where the metallicity is lower. Scowcroft and collaborators obtained a gamma coefficient of -0.26 plus or minus 0.1 in M33. So I think we're ready now to go on and calibrate the different distance indicators to obtain our estimate of the Hubble constant, which Wendy will take you through.
I feel like we're trying to do the dance that we saw yesterday, but that was much more enjoyable. So here's I'm going to start with our summary, our final conclusions, and how we got to the Hubble constant. I'm showing on one slide the log of the distance as a function of log of the redshift. But what was novel about this plot was that for the first time, it was possible to put all of the different methods for measuring distance on the same plot and actually have them fall with a slope that was consistent. And if this plot had been made in the early 1980s, then even the Cepheids that are shown in the open blue circles locally, as I said earlier, had a factor of 2 discrepancy in many of the measurements that had been made. Even showing points from the Sunyaev-Zeldovich effect, the large, filled black circles with the error bars shown to the upper right. And at the time before these results were published, there was some indication that the so-called physically based distance methods appeared to give a lower value of the Hubble constant. What turned out to be the case in the end, although the uncertainties in some of these physically based methods are still somewhat large because they depend on assumptions about the objects being observed, there's also the added assumption that the underlying cosmological model was known. The underlying cosmological model at the time was a flat universe with a matter density which was equal to 1. And once that cosmological model was replaced with the discovery of dark energy, those values of the Hubble constant actually increased by 10%. It was an implicit assumption in that method. So what's also being shown is the type 1a supernovae. Those are the points in green that extend out now to very interesting distances beyond which peculiar motions end up being a complication in the determination of the Hubble constant. So the local Cepheids, the scatter is large. That's not because of distance errors, but that's because of peculiar motions in the velocities. But again, the slope is consistent for all of these distance indicators. So the other part that begins to give us confidence is, as we saw before, the rungs of the distance scale ladder in the past didn't overlap. And one of the things we really paid attention to was trying to make sure that we had multiple distances to many galaxies using different techniques, so that ultimately we were convinced that we had a robust estimate of the errors. So let me back up and look at the local flow. I'm showing you at the top left the original observations by Edwin Hubble in 1929. These are the data that showed that there was an expansion of the universe. He plotted velocity, interestingly, in kilometers. In 1929, perhaps they measured velocities in kilometers rather than kilometers per second, we're not sure. As a function of distance in parsecs. He went out to the Virgo cluster, but at that time the distance to the Virgo cluster that he obtained was at 2 megaparsecs. He had distances to 6 galaxies based on Cepheids, and then the other distance measurements were made by assuming that the luminosities of the brightest blue stars in galaxies had a common upper limit. Those blue stars turned out they were H2 regions, in fact, and that did not turn out to be as reliable a method as the Cepheids, which have persisted, of course, until now. One of the other complications in measuring the Hubble constant, of course, is to get out beyond the distances where peculiar motions dominate, and we now have a much better view of the local universe. The bottom plot shows, on the left, shows the local distance scale from Cepheids alone. So there's still, of course, a lot of scatter, but the slope is consistent with what we get in the far Hubble flow. And so this just is a comparison of our own results. So this is now a linear scale velocity as a function of distance, and Hubble's original data actually fit within that first tick mark, which is interesting. But of course, the secondary distance indicators are not done with Hubble. These are measurements that are done from the ground, which, as Rob says, we will acknowledge shortly. So for the key project, we undertook to calibrate several different methods, the type 1a supernovae, the Tully-Fisher relation, the fundamental plane for ellipticals. Of course, the Tully-Fisher relation, just to remind you, is this relation between the luminosity of a spiral galaxy and its rotational velocity. Fundamental plane is similar for ellipticals, but defines a relation between the luminosity and surface, the velocity dispersion and the surface brightness within a defined effective radius. And then the surface brightness fluctuation technique developed by John Tonry. I'll show you further in a moment. And this is now a comparison of fundamental plane versus the surface brightness fluctuations. Again, for the first time, it's been possible now to compare the distances to individual galaxies using very different techniques. The comparison of the type 1a supernovae versus surface brightness fluctuations, that now show very good agreement amongst these very different distance indicators. So here's the calibration of the Tully-Fisher relation that we did. We lost the symbols again. I apologize for that. This is a study that was carried out, led by Shoko Sakai, who was one of our postdocs for the key project. For each of the distance indicators, we had different group leaders to carry out the analysis. And there were 21 galaxies with Cepheids that we discovered or that had been obtained previously from the ground that were sufficiently, where the overlap with the Tully-Fisher relation was such that we could use them as calibrators. We had optical photometry out into the near infrared. The dispersion of the Tully-Fisher relation is 0.3 magnitudes. And applying our calibration to the Tully-Fisher relation, we obtained a value for that technique alone of 71 kilometers per second per megaparsec. What we did do is divide our errors so that we weren't simply adding things in quadrature. I'll say a bit more in a moment about how we obtained the errors. But the statistical uncertainties are small. They're plus or minus 3 kilometers per second per megaparsec, and we're still dominated by the systematics. And that's true ultimately for all the methods when combined. Here's the calibration of the fundamental plane for elliptical galaxies. We looked at galaxies in 3 groups or clusters, the Leo 1, Virgo, and the Fornax cluster. And this was a study that was carried out by Dan Kelson and our group. That gives a slightly higher value of the Hubble constant of 78, and the statistical and systematic uncertainties are also shown. And then for the type 1a supernovae, this is an area where around the time of the key project had developed very rapidly with the discovery of this relationship between the luminosity of a supernova at its peak and the rate at which it declines in luminosity. That was a relationship established by Mark Phillips. And the dispersion in the period in the supernova Hubble diagram amounts to 0.16 magnitudes, which is 8% in distance. It, of course, is the distance indicator that extends the furthest and enables us to measure the Hubble constant in regions where we are not dominated by peculiar velocities. That method gives a value of the Hubble constant of 71, again with the statistical and the systematic errors shown there. So let me say a few words now about systematic effects in general, which again was the heart of the key project, was to try and quantify those and to ensure that the value of the Hubble constant that we measured was it had systematic effects as minimized to the extent that we could. Reddening, of course, is a big issue if you don't correct for it. As I described earlier, we built into the project observations at V and I wavelengths, allowing us to correct for that. But we wanted also to check that those reddenings were well measured with V and I photometry alone. So we went back when NICMOS was installed on HST and got H-band observations for a subset of the galaxies close enough to actually make accurate H-band measurements. And this is for the galaxy M81 comparison of the VI and H-band moduli and the reddenings that we obtained, which agreed to 1% empirically. So that did work well. and reddening, I think, is not a serious systematic effect we can correct for it. Jeremy has already told you about the metallicity tests. We had other opportunities to test the calibration and the 0 point of the Cepheid period luminosity relation. And for example, what became possible ultimately was to measure the distance to NGC 4258. This is a galaxy with known water masers orbiting a central black hole in the galaxy, for which it's possible to make measurements of the Keplerian rotation curve for the galaxy. They've actually measured directly accelerations for these masers within the galaxy, and also proper motions, which effectively gives you a geometric measurement of the distance to this galaxy. Several groups subsequently have measured distances to the galaxy using the tip of the red giant branch, using Cepheids. There is, again, agreement at the 10% level. It provides a very nice calibration because it's a spiral galaxy that has properties in common with many of the galaxies we observe with the Key project. A big issue, again, locally, historically, in the distance scale, because long period Cepheids are rare, there aren't very many in the local neighborhood, solar neighborhood, where parallaxes can be measured with very high precision. And so the what we did for the Key project was essentially to use the Large Magellanic Cloud, our nearest neighbor, as the calibration, and where the slope could be empirically very well determined. And the distance could be obtained to that galaxy using a number of different methods, again, to average over systematics. A recent check, Fritz Benedict and a group of us obtained parallaxes with the fine guidance sensors on HST, and for the first time it's been possible to measure accurate parallaxes for a sample of 10 Milky Way Cepheids. And this is showing the period luminosity relation using the reddening corrected, the W magnitude for this sample in the Milky Way, showing very good agreement with the slope that we adopted for the Key project. Differs slightly from the work of the Sandage et al. Group, but again, a very powerful test of the overall calibration of the Cepheid distance scale. This is one of the nightmares that I always had. Historically, when Botta, of course, discovered that there were two populations of Cepheids and the entire distance scale changed by a factor of 2, it's that local calibration that can really come back to bite you. But that now seems to be very well determined. And that will, of course, improve in future with future measurements from Gaia and perhaps from SIM. The other issue was velocity flows and getting out to sufficient distances that the peculiar motions did not dominate the error bar in the determination of the Hubble constant. And those are at the 1 to 2% level at the 30,000 kilometer per second distances that the supernovae extend out to. So again, no longer an issue where you could just attribute a different value of the Hubble constant to only observing locally where peculiar flows could dominate. So here are the combined results from the Key project. We did this in a number of ways. We did simulations to understand how the different error components contributed to the final uncertainty. We did a number of different approaches to combining the errors, including Bayesian statistics, simple frequentist statistics. What's plotted here is the relative probability density distributions for the different methods that we used. And so each of these Gaussians here represent the statistical uncertainties for each of the methods. The bars indicate the systematic errors, and these are the solid line that includes all the data is the cumulative probability distribution for the different methods. Fortunately, having done the analysis in many different ways, I think one of the strongest conclusions that comes from analyzing these data is that the overall result does not depend on the statistical method that you choose, and that of course, gives us, again, more confidence in the method. The overall value that we determined was 72 with a statistical uncertainty of 3 and a systematic uncertainty of 7, so we did effectively achieve the 10% uncertainty that we set out to measure. So let me now turn it back to Rob.
Jeremy just said I get the fun part. So we're almost finished. In a few minutes, a couple minutes, Jeremy will talk about, you now have heard essentially the story of our project, and Jeremy will conclude by telling us what's happened in the 10 years since our project was completed and what we can expect in the future. In the meantime, I want to spend a couple of minutes to introduce you to our team and other people who played a critical role in this work. When Jim Peebles phoned us all last spring to inform us of this wonderful news that we had won, he emphasized that, of course, we were being recognized in our own right, but moreover that our work was being recognized as the culmination of the work of an entire generation of astronomers. This was a huge effort, a team effort for us, and an effort of many teams. So this is a team picture from a meeting we held at the Aspen Center for Physics as we were pulling the results together. And let me talk about a few other specific people in more detail. We didn't do this all alone, and there are other people who had major roles, even if they didn't carry the title co-PI. You've heard from Wendy already about Barry Medor's many contributions on designing the Cepheid strategy and actually the whole interpretation of the Leavitt law results, and I'll actually not repeat that in the interest of time. I do want to mention a couple people whose names have only come up briefly, Peter Stetson and Abhi Saha. They had the daunting task of designing photometry software, two independent pipelines that could deal with Hubble images that were spatially undersampled to measure, in many cases, over 100,000 stars on a single image and find the needles, the 2 or 3 dozen Cepheids, the needles in the haystack, and separate them from millions and millions and millions of cosmic rays, which drove us insane in the process. And they did this on VAX computers, software that can run on VAX computers and first-generation Sun workstations. It's a lot easier now. It was a remarkable achievement then. And their software is the foundation of what we accomplished, and the foundation of, I think, most stellar photometry with Hubble today. Those programs are their derivatives since. As Wendy mentioned, the penultimate product of the key project was the calibration of the 4 main secondary distance indicators. We actually delegated that work to 4 people who were postdocs on the team at the time who had distinguished themselves in the less glamorous work of finding Cepheids over the years in between. Shoko Sakai, who's now at UCLA, did the Tully-Fisher calibration. Laura Ferrese, now at DAO, actually did the surface brightness fluctuation, 0-point calibration, and compiled an immense database that was used for all of the other work. Brad Gibson, now professor at University of Central Lancashire, Preston, headed up the Type 1 supernova work. I should mention that the supernova Hubble data came from a team led by Alan Sandage, involved people in Baltimore, Pasadena, and Basel, and the work we were able to actually benefit from including those data in our analysis, and Brad did that. Finally, Dan Kelson, now at the Carnegie Observatories, did that. There's another Bill Gates glitch there that should say D subscript N sigma relation, calibrated the fundamental plane using observations of nearby groups and clusters. Also, Ming-Sheng Han and Lucas McCree, whose picture you'll see in a minute, contributed very valuable elements to this work. The people who did most of the labor, most of the hours in this project were spent by people crunching Cepheids. All of us, I think, all 3 of us got in, rolled up our sleeves for this, but the vast majority of work was done by mainly a set of postdocs. There was one very seasoned veteran, John Graham, who actually jumped into the fray. Most of the other people were postdocs hired onto the project. I won't go through their names individually, but say that the foundation of our project were very solid Cepheid distances to galaxies, and these folks operating one pipeline or another took those analyses to fruition and wrote the key papers of the key project. Finally, you can't be successful without some senior mentors and movers and shakers, and we had our share on the project. They provided guidance, leadership through the project. I would call in particular John Huckra, who did far more than that. He actually went to the telescope, helped obtain a lot of the data that we used to calibrate the Tully-Fisher relation, and with Dennis Siritsky and I measured metallicities, gradients in most of the galaxies, so we could apply the Cepheid metallicity correction. So I hope you will not now leave the auditorium with the notion that we did all the work. Our team, this was a team effort, and these people were all critical. Also, please do not leave the auditorium thinking that our team solved it all by ourselves. This involved a confluence of efforts, in particular in calibrating and laying the groundwork for the secondary indicators by a whole host of people. I'm sure I've left many important people out, but I want to call out Martha Haynes in particular, because I know Martha's sitting over in the corner. She and Riccardo Giovanelli did, along with Brent Tully, Mike Pierce, and others, did much of the foundational work on the Tully-Fisher calibration that we used. And there were people, we were able to essentially gather a vast storehouse of work from other people. I won't go again, read the names. A few names I'd like to pick out in particular. As I've mentioned already, the supernova data came from a team led by Alan Standage and Gustav Tamon, so there's direct DNA sort of in our result from their labors. But also, of course, the whole methodology that we developed, the whole concept of the distant ladder, owes immensely to Gerard de Vaucouleurs, Alan Standage in particular, for work on the decades that really contributed mightily to our work. So, again, so this should really be seen as a team effort in the broadest sense. Probably all told at least 100 astronomers in the end, making vital contributions to what we were able to actually consolidate in the end. Jeremy, you can finish.
Well, I'm starting to like this tag team approach, because one of the things you can do while you're sitting down is you can think, oh, what did I forget to tell them last time? So one thing I forgot to tell you was that when we apply the metallicity calibration to the Cepheid period luminosity relation, it reduces the Hubble constant by 4%. That's the size of the effect. Now, I'm going to spend more time talking about the recent past than about the future and finishing off our presentation this afternoon. Wendy's already mentioned the wonderful galaxy NGC 4258, which has a maser disk rotating around the supermassive black hole at the center. And since it's possible using VLBI techniques to measure the proper motions of these masers as well as the velocities, this yields you a geometric distance for a galaxy which fortunately has Cepheids as well. And so that allows you to take a different approach to calibrating the Hubble constant. As you know, we assumed that the Large Magellanic Cloud was at a distance of 50 kiloparsecs, and that's the foundation of the result of the Key project. But just looking at the distance of NGC 4258 from geometry, the Herenstein et al. Paper gives you a distance of 7.3 megaparsecs, and from Cepheids, work by Lucas McCree and calibrators, gives you 7.5 plus or minus 0.3 megaparsecs, so good agreement there. But alternatively, you can make, instead of the Large Magellanic Cloud as the foundation of the project, you can make NGC 4258 and its geometric distance the foundation of the project, and that then gives you a Magellanic Cloud distance of 18.4. Now, others have gone on in what's called the Mega Maser Cosmology project to find more distant masers, and this in time will allow us, or will allow them in that project to obtain a value of the Hubble constant based upon Mega Maser galaxies. And we await that with interest. NGC 4258 can be made the foundation of the distance scale in another way, and a very nice project recently published just a few weeks ago by Adam Rees and collaborators is called the Supernova and H0 for the Equation of State project, and there what they have done is to measure Cepheid distances to supernova galaxies, some of which are Key project galaxies as well, and measure relative distances of those galaxies to 4258. And this allows many of the systematic errors to cancel out, since we're only dealing with differential distances within the Cepheid database. and in combination with 240 supernova type 1As at redshift less than 0.1, they're able to emerge from their project with half the uncertainty of the key project and an H0 value of 74.2 plus or minus 3.6 kilometers per second per megaparsec. It also yields a value of the equation of state parameter, where -1 is the general relativistic value of minus 1.12 plus or minus 0.12. And that's where this subject is going at the moment. Another confirming result that is really all important in cosmology and has done more than anything, I think, to realize the goal of precision cosmology is the WMAP experiment, whose anisotropy you can see on the screen behind me at the present time. And it's possible to calculate the size of those anisotropies. It's simply the sound horizon on the surface of last scattering, and to obtain a value of the Hubble constant from that. There's the power spectrum of the temperature fluctuations, and it's that first peak that it's possible to calculate using the sound horizon calculation. And so how you get H0 from WMAP in a simplified version at least is first of all to calculate that sound horizon. It's 143 plus or minus 4 megaparsecs. You measure the size of the angular size of the first acoustic peak on the diagram that I just showed you, and that of course is equal to the ratio of the sound horizon and the angular diameter distance. So putting all those things together, you get an angular diameter distance of 13.7 plus or minus 0.4 gigaparsecs for the distance of the surface of last scattering, and entering that into the integral definition of the angular diameter distance, and evaluating that integral there from 0 to the surface of last scattering redshift there, the integral being that 3.185 number there in the numerator, you get a Hubble constant of 70 kilometers per second per megaparsec, a very fine confirmation of the work of the key project and something which stands alone as a calculation of the Hubble constant. So to complete, I want to say one word about the future, and that is we can look forward to a time when when proper motions are to be measured even for stars in distant galaxies, or at least in the galaxy M31. And on the right there you can see the SIM light satellite which will do that, and on the left you can see stars in M31 moving at 50 microarc seconds per year, but also moving at 200 kilometers per second. So by fitting a circular flow model for the stars in M31, it'll be possible using SIM's accuracy, which will approach 1 microarc second, to obtain a rotational parallax and a distance to M31 and M33 of 1% accuracy. And that will really do wonders for the Cepheid distance scale, because we'll be comparing galaxies which are like M31 and M33 to larger distances, thus removing more of the systematic errors. So with that, I want to close on behalf of the three of us and say thank you for NASA. Thank you to NASA for designating this a key project for HST and allowing us to get the work done. Thank you to the team whom Rob has introduced to you so well for making it a success. And thank you, Gruber Foundation, for recognizing this work.
Thank you very much for this fascinating and I would say very modest presentation. I think you've been really careful all the time to try to show that you were just participants in a big adventure. It's really a human adventure, you know. How fast is our universe expanding? Everybody wants to know. But of course, we all know that your participation was more important than you tried to make it appear. So we really commend the Gruber Foundation for giving you this well-deserved prize. So are there questions or comments from the floor? I really don't see very much, so please stand up. Yes.
Maybe everybody wants lunch.
Or maybe everybody wants lunch. It's true, because the session starts again in a quarter of an hour. So I think, yes, we thank you all, and we thank the speakers.